in January.
Very good. Okay.
There will be a conference. There will be a conference on highly frustrated magnetism.
Very good. Okay.
Yeah, Yasir Iqbal. Yeah, Professor
Yeah.
Yasir Iqbal told that you're coming here in
Yeah.
January. Yes, good. Nice to.
I plan, but before that, I have to visit small Russian-Indian workshop organized by Tanusri Shahadasgupta.
Okay, in Kolkata.
Not Kolkata, but in Goa.
Oh,
Kanunga
Goa.
Shudipta Kanungo
Okay.
will organize a small workshop.
Enterprise go.
Okay. Good.
But Tanusri is one of the main organizers.
Okay, very nice. Yeah. You talk to him. Yeah, you can. Yeah.
Hello, how are you?
Nice to meet you. I am happy
Thank
to
you.
meet you.
Thank you very much for accepting our invitation.
I remember my visit to Chennai. It was just pleasure, just quite interesting.
Yeah.
Okay, see you again in January.
Yeah, in January, for a few days, I will be in Chennai.
Hello.
I plan at least. So we still have a couple of minutes, right?
Yes. Yeah.
So you will tell me when to start.
Yes.
Okay.
How come if you don't see? Ramakrishnan.
Sorry. Hello.
Hello,
Hello.
Siva. Suri
Sorry,
here.
Professor.
Yeah.
How are you?
Fine.
Hello, Professor Suri. Nice to see you. Hi.
Thanks a lot.
Suri, switch on your video because I cannot see you. I only can.
Yeah, I don't know.
hear
I
you.
suddenly put on something and it says download something new and it'll be wasting time. Go ahead, doesn't matter.
This one, huh?
Sip of coffee.
Professor Suri, your video is not on.
Yeah, I don't know. Suddenly it switched on to the Russian. I was switching on to your ID.
Oh,
Don't bother, please, don't bother.
okay. No problem. Yeah.
Sometime in that 10.
उसके लिए बोले वीडियो होगा।
Should I switch my screen this way? It is better. Is it okay?
Yeah, it's okay. It's not in full screen. Okay. Yes.
Okay,
Yeah, looks fine. Yes.
good.
Go.
Yeah.
See.
Hello, everyone. Good evening. Welcome to today's quantum talk by Professor Alexander Vasiliev from Moscow State University. We're very happy to have you here, Professor Vasiliev. Good to see you. And we'll, of course,
Thank
be
you.
meeting you physically in January when you come here, visit us for the conference. And I request my colleague, Professor Setupati, to introduce the speaker.
Very good afternoon.
Oh, he's studying there.
Very good afternoon. And I have the pleasure of introducing the speaker for this evening, Professor Alexander Vasiliev. He's a distinguished professor in the Department of and head of the Low Temperature Physics and Superconductivity Lab, and head of the Functional Quantum Materials Laboratory at Moscow State University, Russia. He received his PhD and Doctor of Science from Moscow State University, Moscow. He is a pioneer in the strongly correlated electron systems, macroscopic quantum phenomena, and quantum magnetism. Professor Vasiliev has published more than 500 papers in peer-reviewed international journals and 3 monographs. He has been a visiting professor at a large number of institutes and universities all over the world. And to name a few, he's the visiting professor at UIUC USA, Tokyo University, Tohoku University in Japan, and Cologne University, Germany, and University of Paris in France, and IFW in Germany. He is one of the members of the Control Committee of the Ministry of Science and Education on the Russian Federation. And Professor Vasiliev has received several prestigious awards, including the Sign of Honor, Russian Ministry of Education in 2005, and M. Lomonosov Prize for Science in 2013, State Award Medal in the Order of Merit in 2021. And today he's going to talk about the spin liquids. And it's over to you, Professor Vasiliev.
Okay, should I start? Should I start?
Yes, Professor, you can start. Vasiliev, you can start now. Yes.
Okay, thank you for the introduction. I am very happy to be with you today and present some of our recent research. On this first view graph, you see our university. Sometimes we call it Temple of Science. And it is situated in Moscow. It is the biggest university in Russia. And one of the departments of this university is low temperature physics and superconductivity, where we conduct various measurements on spin liquids. Let me first give some definitions of what is a spin liquid. Spin liquid, it is a phase of matter that can be formed by interacting quantum spins in certain low dimensional and or frustrated magnetic materials. There are some characterization of spin liquids. They are characterized by their long-range quantum entanglement, fractional excitations, and absence of ordinary magnetic order. And last thing that I wish to say at this view graph, that spin liquid can be or not can be protected by a spin gap. So we distinguish different spin liquids, either with gap or without gap. And I will give some examples of these systems. But first of all, I wish to present some basics. Low dimensional magnetism is based on some definitions which I show here. And first of this definition was given by Ernst Ising that in the case of one-dimensional magnet, Ising magnet, which means it possesses only one component of the magnetization, the chain of spins is ordered only at absolute zero temperature, which is impossible to reach. 3 years later, there was a definition by Werner Heisenberg that in the case of one-dimensional Heisenberg magnet, which possesses 3 components of the magnetization, the chain of spins is not ordered even at absolute zero temperature. And finally, there are many definitions concerning low-dimensional magnetism, but I choose only these 3. The last one, it is made by Lars Anzager in 1944. And in this case, it deals with 2-dimensional magnets. A 2-dimensional Ising magnet is ordered at temperatures comparable to exchange interaction parameter. And 2-dimensional Heisenberg magnet is disordered at any finite temperature, but ordered at absolute zero. Important here is that Ising magnet, if it is 2-dimensional, can be ordered just similar like 3-dimensional magnets are ordered. So let me present some examples of various systems which possess either gapped or gapless spin liquid. And I will start with half-integer uniform spin chain. Half-integer, it can be, for example, kappa 2 plus system with spin equal to 1/2. So for this chain, there is no gap in the excitation spectrum. And when we study temperature dependence of magnetic susceptibility, we can expect a broad hump at temperature comparable to leading exchange interaction parameter J. In fact, it is something like 0.64 of main interaction parameter. At zero temperature, magnetic susceptibility is reduced by about 15%. A low temperature upturn, it's usually ascribed to impurities, but this impurity tail can be efficiently suppressed by external magnetic field, a purely one-dimensional system. In real life, we have interchain interactions, so we can expect that half-integer uniform spin chain will order at sufficiently low temperature. Concerning Ising chain, it demonstrates a broad hump in magnetic susceptibility at about 1/2 of exchange interaction parameter. And magnetic susceptibility reduces to 0 at 0 Kelvin. So we can, in fact, distinguish between Heisenberg behavior and Ising behavior and understand to which class any system belongs. So there are many good examples of uniform Heisenberg spin chain, spin 1/2 chain. Among them, this alkali earth copper phosphates. This was done almost 20 years ago. Most recent example of this research in this direction. This paper has been published this year. And if you look at magnetic susceptibility curve, it looks like ordinary paramagnetic behavior, but it is not. It never can be described by Curie-Weiss law. In fact, a very large exchange interaction parameter is present in this system, copper, bismuth, oxygen, vanadium. In this system, which is similar to mineral namibite, copper is magnetic and vanadium is non-magnetic. So this huge exchange interaction parameter, like more than 500, makes the behavior of spin liquid very hidden. It simply looks like Curie-Weiss, like paramagnet, but it is not. So according to my knowledge, it is one of the last uniform half-integer spin chain observed. Next one is half-integer alternating spin chain. Alternating means that most probably the distances between spins within the chain are different, they alternate. And so this alternation finally results in the appearance of spin gap. Alternating spin chain can be described by two different exchange interaction parameters. Depending on alternation, one can consider two limiting cases. If we consider alpha equal to 0, it means that we broke our chain into a set of isolated dimers. And dimer itself possesses a gap between ground state and excited states. At other limit, at alpha equal to unity, this is uniform chain. The spin gap depends on the value of this alternation parameter, but in any case, we have spin gap behavior distinctly different from those of uniform chain. Magnetic susceptibility shows correlation maximum, which shifts from 0.64 J1 at alpha equal to 0 to lower T. Alternating spin 1/2 compound with a large spin gap is written here, chemical formula, also discovered 20 years ago. For spin gap materials, usually the impurity tail is very well expressed. However, it can be, of course, suppressed by external magnetic field. And finally, concerning those uniform chains, it is a chain created by integer spin. Integer uniform spin chain possess spin gap. This gap was predicted by Duncan Haldane, and observed in many materials. So it is another type of gapped chain spin system, and for that, nickel is very suitable because nickel 2+ possess spin equal to unity. The value of gap relates to the value of exchange interaction parameter, like 0.4 of exchange interaction parameter. This example of the Haldane chain was observed even longer time ago, something like 25 years ago. Note that Haldane prediction, Haldane conjecture, was made in 1983. After that, many attempts were done to find confirmation of Haldane theory. And very different inorganic and organic compounds were checked for this property, for the presence of Haldane chain. So these chains were subdivided into long-range ordered, dimerized, large D, which means large anisotropy, and Haldane phases for spin 1 chain compounds. Recently, my co-workers and me wrote a review paper on Haldane compounds, and they are shown on this so-called Sakai-Takahashi magnetic phase diagram. You will see that Haldane sector in this paper contains only 7 different compounds. 3 of them are organic and 4 inorganic. And these Haldane chain compounds can be based on either nickel 2+ or vanadium 3+. Both elements will possess spin equal to unity. Recently, very recently, it is just not published yet. Another compound was synthesized with this chemical formula, and the carrier of magnetic moment is vanadium 3+. Vanadium 3+ organize a chain running along B direction of the crystal structure. And the study of these compounds continue even now, even today. But we see that magnetic susceptibility shows broad hump, which is a signature of spin gap. Specific heat does not show any indication for the long-range order. It's very smooth. It is shown in the inset to upper view graph. And when we subtract the impurity contribution, we can see that experimental curve can be fitted by formula for the Haldane chain. Even more, we applied a relatively strong magnetic field of about 30 Tesla, and we were able to close the gap by external magnetic field. So it is brand new Haldane chain compound. So now I probably prefer to make a brief stop, because I will turn now to next section of my talk, and if you have questions concerning this part, I will be happy to answer. And it will give me a short break for 3 minutes. Are there any questions to me concerning those chains, uniform, alternating? Dear colleagues. I do not hear any questions. Do you have questions? If not, I will continue, but please answer me.
Yeah, please
Please go ahead. You can go ahead. We will have the questions at the end, Professor Vasiliev.
Excellent, excellent. So now I will turn to the second part of my talk, and it will concern the methods how gapless chain system can be converted into gapped system, a system with the gap. So I will give just 3 examples how uniform chain system possessing no gap will transform into non-uniform system with a gap in magnetic excitation spectrum. Most famous example of such behavior, it is a spin-Peierls transition observed 30 years ago in copper germanium oxygen 3. At this transition, crystal lattice dimerizes. The loss in elastic energy is compensated by the win in magnetic energy. It is extremely rare. Everything now will be extremely rare because very few compounds can pretend on spin-Peierls transition. You see that magnetic susceptibility drops down along all directions at 14 Kelvin due to this dimerization of previously uniform chain. There exists also famous analog of spin-Peierls. It means just Peierls transition. It is metal insulator transition with opening of the gap in energy spectrum of electrons. So it is spin gap formation mechanism number 1. Next one is the spin gap formation in sodium vanadium 2 oxygen 5. Please note that vanadium in this compound is mixed valent. Formally, its valence is 4.5. And at high temperature, this uniform chain exhibit standard behavior of one-dimensional system. But at 34 Kelvin, charge disproportionation occurs. Vanadium 4 plus and vanadium 5 plus separate. They took their own places. It's no more uniform system with intermediate valence, but it is charge ordered system. And ordering of this charge also introduce alteration of the spin exchange along the chain. So it is second example of the spin gap formation discovered by Isoba and Ueda in 1996, also a long time ago. I do not remember. Probably there are more examples of such behavior, but it is most brightest. So first mechanism is spin-Peierls, second charge disproportionation, and finally there is also third mechanism how to create spin gap in the uniform chain. It is possible to do by orbital ordering. Now we have sodium, titanium, silicon 2, oxygen 6. And titanium in this compound is 3 plus. So it is spin 1/2 system. At elevated temperature, it is uniform chain and 2 equivalent orbitals are occupied by the same, this electron, one electron. But at very high temperature of about 210, there will be a kind of Young-Taylor transition, and electron will decide which T2G orbital to occupy. And it will result that at one step of this chain, there will be a strong exchange interaction. At second step, it will be almost zero. So this uniform chain transform into set of dimers. And dimers, once again, possess this large spin gap between ground and excited state. This research was done by Isobe and your lecturer, and it was a long time ago, more than 20 years ago, when I was visiting Institute of Solid State Physics in Tokyo. And so it is end of second short part of my presentation, and now I have to turn to the another third part of my presentation, which is how to say most actual. We work on those compounds which I will mention now very actively. So it is so-called square Kagome lattices. Square Kagome lattices looks like something very unusual, because everyone knows that Kagome, it is hexagonal network. And Kagome lattices are in the focus of research in the field of frustrated magnetism. It is presumed that Kagome lattices host spin liquids, and it is debated, hotly debated, whether there is a gap or whether there is no gap in magnetic excitation spectrum of the Kagome lattices. But I will not speak about Kagome lattices, but I will speak about square Kagome lattices. In fact, there are very many ways how to cover the surface with polygons. And I will consider only those situations when we deal with corner sharing triangles. So in the left, you see the Kagome lattice. Probably everyone knows this lattice, and it is shown how it can be created by corner sharing triangles. For Kagome lattice is characterized by hexagonal voids and number of nearest neighbors for any ion equal to 4. But it is also possible to rearrange these units of Kagome to make so-called Sorel net. And it is shown on the second picture. And for nearest neighbor, now it is 2 cases. Number of nearest neighbor can be either 4 or 6. Third one case, one can arrange those corner sharing triangles in a way shown on the third picture. It is called so-called L4 net. And in fact, I do not know whether we have experimental realization of the second and third cases. I am not sure. Maybe there is experimental realization or not. I even did not check because I was focused on the last one shown on the right side of this view graph. It is so-called square Kagome network. It is different from Kagome. You see that originally we have a square. A square is shown by red color. Then we draw a triangle on the each side of this square. And then we connect these triangles by vertex, by corner. So it will be so-called square Kagome network. For A position and for B position, it's also for neighbors like for ordinary Kagome, but it looks different. Analysis of these networks was done 10 years ago by Van den Brink and other people and published in Physical Review B. So for very long time, it was only game for theorists because no experimental realization of square Kagome lattice was suggested. In fact, square Kagome idea, it is a rare case when it is possible exactly establish origin of this new physical concept. In 2001, Indian scientist Siddharthan, working with French scientists in Paris, Siddharthan and George, introduced this two-dimensional network. And even in this paper, it is written that it's namely Siddharthan invented on the end of his pen this symmetry. Maybe he was making some picture on the piece of paper and arrived to this network 20 years ago. So they published paper in Physical Review B 22 years ago and predicted that there will be many singlet states. There will be a gap between singlet and triplet. They also predicted that specific heat will show two peaks. They also predicted a plateau 1/3 in magnetization. So it was original theoretical paper published 20 years ago. And since that, for 20 years, there was nothing. 20 years, there were very many theoretical papers discussing different aspects of this model. Theorists considered different variants of behavior for these square Kagome lattices, but no experimental confirmation was observed. Ralka and Rusatsatzakis in 2015 considered what can be ground state and excitations of these square Kagome lattices, and they arrived to different loops. And these loops are shown here. It is pinwheel left panel, loop 6 right panel. In any case, it is valence bond crystal with different singlet states, with different ground states. It means that they considered that it is not only transition from singlet to triplet, but also singlet transitions are possible. Okay, so 20 years of theoretical research, and after that, finally, researchers in different countries started to realize that there are experimental realizations of this QuCenDiEM lattice. So, in fact, in geology, there are few minerals known that possess QuCenDiEM lattice, and these minerals are written here. It is nabocoid, and you see that it is kappa 7. Kappa 7, it is a little bit more than needed for QuCenDiEM lattice. To create QuCenDiEM lattice, 6 kappa will be enough. So 1 kappa is extra in nabocoid. Then there is atlasovite, elasmochloride, and fauroid. If you look at atlasovite, you will see that there is 2 magnetic ions, copper and iron. Potassium, copper 6, iron, bismuth, so on. If to study this compound, most probably property of iron will influence the property of compound, and spin liquid behavior will be hidden. So Japanese team recently synthesized synthetic counterpart of atlasovite. It is potassium, copper 6, aluminum instead of iron. And in Moscow University, Larissa Shvanskaya and co-workers synthesized synthetic compounds, sodium 6, copper 7, and so on. Here you see how this square lattice is organized. On the left, you see natural single crystal, and on the right, you see the single crystal created in geology department of Moscow State University. Both looks beautiful. Now what we have concerning experimental study. Concerning experimental study, I show here on the left temperature dependence of magnetic susceptibility, and we cannot say from that whether there is a gap or no gap. Concerning specific heat dependence shown in the middle, it is no long-range order. It is okay, spin liquid does not need long-range order, but joint research was done with Chinese group, and we found that these compounds, these synthetic compounds, show no magnetic order down to 50 millikelvin. But there is a contradiction between theory and experiment. Theory predict 2 peaks in specific heat. One should be at low temperature, another at high temperature. Probably we cannot see high temperature peak in specific heat due to phonon contribution. But clearly, there is no extra peak in specific heat down to ultra low temperature. So there is a contradiction between 20 years of theoretical research and first experimental paper. The same was observed by Japanese team on this atlasovite. Also, they cannot claim whether there is a gap or no gap, and no peak in specific heat has been observed. So, in fact, it is kind of very dangerous situation. Many theoretical research claims that it should be this special anomaly for QuCenDiEM lattice, and first experiments do not present it. So my last view graph. In chemistry department of Moscow State University, big family of square Kagome lattice compounds was synthesized, similar to natural mineral. The chemical formula is written here. An alkali metal can be anything from sodium to cesium. Once again, there is extra kappa. Kappa number 7 is not needed at Kagome lattice. If you look at this picture, here it is extra kappa. Kappa 2, it is out of square Kagome lattice, and it can possess its own life. So what we observed? We observed the following. Magnetic susceptibility, let me choose potassium compound, shows sharp peak at about 3 Kelvin. This sharp peak is long-range order. Other compounds are similar. But when we turn finally to what is most needed, specific heat, we can see that besides this small peak at nail order, there is extra peak at about 5 Kelvin, which is observed in practically in all these compounds. And as shown in the inset, it is not suppressed by big magnetic field. So we presume, and this paper is now under consideration to be published, that square Kagome lattice possess spin liquid property and show this broad peak in specific heat at about 5 Kelvin. Extra kappa external to the square Kagome lattice possess its own life and orders at 3 Kelvin. This small anomaly can be suppressed by very small magnetic field. So probably it is first confirmation of 20 years theoretical research concerning Kagome square lattices. Now it is 45 minutes, which is academic hour, and I wish to say thank you.
Thank you very much. Thank you very much.
Very welcome.
Yeah, yeah. The questions from the audience.
Hello, sir.
Yes, yeah. Yeah, please go ahead.
Sir, can you go in the 18 slides?
Slide number 18.
Yes, sir.
Yeah.
Slide number 18.
Yes.
18, here it is. Yes.
Sir, here in the third graph, CYT versus T, but in the lower curve, there is a something, I cannot understand this. There is the graph is increasing in the lower line. What it represents?
You mean lowest picture from the left, right?
Yes.
Yes, sir. Yes, sir.
Yeah, specific heat. It is nuclear contribution. It is so low temperature, below 50 millikelvin, that the nuclear specific heat comes to play. It is not related to electronic subsystem. This upturn at lowest temperature is not ascribed to electronic property, it's a nuclear property.
So it is for nuclear contribution.
No, it is not electronic, it's another origin. Usually when you reach about 50 millikelvin or so, nuclear degree of freedom come into play.
Okay, sir. Thank you.
You see here, it's the measurements from 2 to 100, and it is very smooth curve, which shows that neither long-range order takes place, no extra peaks predicted by theory are seen. In fact, it's contradiction. It's contradiction which should be solved by joint efforts of experimentalists and theorists.
Okay, sir.
I have no answer why it is not present, but two experimental research made simultaneously in Japan and in Russia show absence of this peak in these systems.
Okay, sir. And in 19 slides, the last slides.
Last slide, you mean 19, right?
Yes.
This one.
There is in the second curve, there are two peaks. Can you say again briefly why there is two peaks?
Exactly, right. So, as I said, chemical formula is written here, and it is alkali metal, copper 7, tellurium, and so on. To create square Kagome lattice, we need only 6 coppers. And copper number 7, it is outside of this square Kagome layers. So we presume that 6 copper ions create spin liquid, but those outside of layers, they have independent long-range magnetic order. And so what we have now, please look at the picture on the right side. You see broad peak at about 5 Kelvin, right?
Yes, sir.
And small peak at about 3 Kelvin. And they are very different with respect to magnetic field. You can apply small magnetic field and immediately suppress the small peak, which we ascribe to long-range order of this copper number 7. And we cannot suppress this broad peak by 9 Tesla, which means if we cannot suppress any anomaly by magnetic field, it should be of some kind of non-magnetic origin. And non-magnetic origin concerning spin liquids, it's only singlet transition, not singlet triplet. Triplet is magnetic. But singlet transition, it is, let me show you slide number 16. It is different singlets. You can look at upper picture and lower picture. It's a different singlets. And it is written also here, pinwheel singlet and loop 6 singlet. So we believe that we observe this singlet transition not suppressed by external magnetic field. That's all.
Okay. Okay, sir. Thank you.
Yeah, welcome.
Mr. Vasiliev,
Yeah.
Setu, just mute that. I have a question about the systems NATI SI206 that shows an
Just a second. You mean this one?
Yeah, exactly. So,
Sodium, titanium, yes.
so are we seeing a reentrant behavior at low temperatures, at temperatures below 100K?
Well, you see, when you have a dimer system, magnetic susceptibility became very low. And so any impurity can produce relatively large Curie tail.
Yes.
So we see a large gap which opens at 210 Kelvin, and it should go, magnetic susceptibility should go to 0. But it is impossible to get rid of impurities. So this upturn is not related to anything else but impurities.
Impurities. Okay. What kind of impurities?
I have no idea. I can say only that it was very difficult to obtain this compound from precursor because we were trying to make it using some chemical route, and it immediately absorb water. In this final form, probably it is not sensitive to water, but I can imagine that magnetic impurity can be, for example, if one titanium is 4+, in this case, another neighboring titanium will be magnetic, titanium 3+, and it has spin 1/2, it's like loose end. So impurity magnetic can be probably just absence of some proper titanium. If it is slightly over-oxidized, it will lead to magnetic impurity. Under-oxidized probably not bad because titanium 2+ can be non-magnetic. I think that this kind of impurity, titanium 4+.
And in that region, 100 to 300 Kelvin,
Yeah.
are there any reports on electrical conductivity on this compound?
No reports on electrical conductivity. This gap is relatively large, so it is insulator.
Okay.
It is insulator, and it shows kind of Curie-Weiss behavior, but not exactly. It's low dimensional.
Okay.
And then Jan Teller in titanium at about 200. It's more or less reasonable. Similar behavior was observed in lithium, titanium, silicon to oxygen 6, but it had much more impurities. I don't know why chemically. So sodium, it is our best system with this transition.
Okay, thank you.
Yeah, very welcome.
Yeah, I just want to ask in the same question. Do you have magnetic field dependence on this? Any variation?
I do not have it with me, but I remember that I measured it. So nothing except impurity response I was able to see because gap is so large. You see transition temperature is 200 Kelvin. So you can imagine that the gap between singlet and triplet state is also huge. So what we can observe, it's only kind of brilliant function related to impurity. Note that there is a very low, in fact, magnetic susceptibility. It is chi multiplied by 10 to the 4. So in fact, it is 10 to the -4. It's very small.
Okay. And then in your slide number 18, once again, we go back.
Of
Yeah,
course.
sorry, yes. Yeah, where you said, or 19, the next one, I'm sorry, 19.
19, okay,
Yes,
okay,
19.
okay.
This is for rubidium, you're seeing the temperature, the magnetic field variation,
Yeah,
the one
just
in the
a sec.
insert. But is it true for all other samples also? The potassium and sodium also?
The same behavior is for all compounds of this series.
But it is interesting to see they are all in the same temperature range, the peak.
Yeah. You know, yes, I agree with you. And you know, the properties of this square Kagome lattice are very similar because the chemical formula is the same. The only thing which is changing, it is alkali ion. An alkali ion separates those layers, but property of the layer basically are the same. And so that is why this peak is observed basically on the same temperature, because we simply separate these layers by alkali metals.
I see. Okay.
Mm-hmm.
Yeah. Any other questions? Professor Suri? Somebody, yeah, please go ahead, Jatin.
Hello, Professor. So you were telling about this orbital ordering is one of the mechanism to open the gap. Like Professor Rao asked in this compound like this NaTiS2O6. Can you go to that slide?
Which one? I show three
Third
mechanisms.
mechanism third.
This one or this one or next one? Which
Next
one?
Next one.
Next one concerning orbital ordering. This
Right. So you
Uh-huh.
told, I mean, here like this orbital ordering is also acting as a like source for opening the gap. Now, how can like experimentally one capture this orbital ordering in the system?
Well, how experimentally to do what?
Like
To
like
tune it is impossible because it is so large temperature that no application of pressure, nothing. You see, we have in fact we have Young-Taylor situation. This titanium 3 plus possess one electron, and this one electron at high temperature sit on two orbitals, T2G orbitals, and the Young-Taylor effect, it's a huge energy. It distorts. In fact, it's structural phase transition, which leads to distortion of the lattice, and this one electron will sit on the lowest orbital.
yeah,
And it will be so that on one step, it will be very strong coupling between two titaniums. On next step, it will be no overlap between orbitals. If we choose XZ, then it will be no overlap over YZ. This chain is so, it's an interesting chain. It's so-called pyroxene chain, a twisted chain. And so exchange is organized on both XZ and YZ orbitals. When only one of these orbitals became taken by electron, another one will be empty and it will provide no coupling. So it is case when Young-Taylor result in formation of magnetic dimers.
So actually, what I want to, know from here that like for spin ordering, people use this neutron diffraction experiment. Similarly, for orbital ordering, is there any experiment to capture?
I not understand question.
So
Please.
for any spin ordering, people generally use this neutron diffraction to have the picture of spin pattern. Similarly, for orbital ordering, is there any particular experiment that could capture the orbital pattern?
Concerning, you mean whether the neutron scattering experiment was done or not on this system? I am not sure. I know that first principle calculations were done in the high temperature crystal structure, low temperature structure, but I am not sure that this orbital ordering picture was confirmed by neutron scattering. I do not remember. Probably everybody agrees that the picture suggested is correct, and that's all. Okay. And you know, it is so huge energy is needed. The transition temperature 200. So the gap between ground state and excited state is also about 200.
Okay, thank you.
You're very welcome.
Hello.
Yeah, Professor Suri, please go ahead.
Oh, yeah. Sorry, finally I saw him.
Yeah. Well, when I was a student, I was so scared to ask a question. Now I'm not. I don't care what you think of me. So I'm going to ask a question. Is there any interest in pressure studies on any of these compounds?
What is the question?
Any interest in applying pressure on any of these compounds? Can we reduce the spin gap?
Yeah. Yes. Probably yes, but not to this quasi one-dimensional systems, but I am mostly interested in square Kagome. We are probably are the only people who possess these materials now. And I am quite interested, in fact, to apply pressure, because I can imagine, let me show this final, once again, this graph number 19. You see that there are low temperature peaks at 3 Kelvin and 5 Kelvin. And I think that physical properties are very different. That lowest one is long range order of spin number 7, and this peak is belong to spin liquid. So they must differently react on pressure. So in fact, I am quite interested to that somebody make a pressure experiment, and we are ready to give a sample.
Okay.
I do not have this facility, fortunately.
Yeah, I have. I collaborate once in a way with Indian laboratory. They apply pressure. We have done something on manganites.
Which Indian laboratories? There are many
it's
laboratories in India.
Yeah, it's in Trichy.
Where?
It's about 300 kilometers south of Madras.
Sir, he's
Well,
a person,
it is-
Tyagarajan, he's there.
There's one Tyagaraja. He's a better person. He will answer you.
He's the person. He's
If
the
I-
person he is talking
if
about.
I
He's
will
very
be
intelligent guy.
connected,
He will answer you.
if I will be connected with these people in advance,
Yeah.
Yeah, Thiago,
and
can you answer?
if people agree to start studying this direction, I simply can bring sample with me to Chennai. Chennai and Madras, in my view, it is just the same.
Yeah, it is
Yeah,
the
yeah,
same. Yes.
Am I right?
Yes.
Yeah.
Yes, it is the same.
So 100 kilometers is not a distance by
300,
Russian
300.
standards.
Yes. Yeah,
Thiago, please tell your maximum capacity of pressure and temperature.
Yes. Hello, Professor. I'm Thiago. We have a collaboration paper with BDD. That's one I have it with Raman and the high pressure exciting measurements at our sample through you.
So we
In
have
fact, it's necessary to organize email exchange to discuss what kind of sample, what mass of sample and so on, and what pressure can be reached. In my view, 10 kilobar will be enough to start studying this direction.
That they can do. In principle, they can do.
We can go
they can go up to 4 Kelvin, I think.
But it is necessary to measure magnetic susceptibility or, well, magnetic
Yeah,
susceptibility.
they measure,
Right.
they have.
Yes, sir. That can be done here even. We can, it's possible. Electrical resistivity under high pressure up to 3 GPa, it's possible. I mean, 40 kilobar.
It is not conducting. It is not conducting.
Okay,
So
sir.
Only
electrical
only the
resistivity will not work.
Okay, sir. Magnetization is possible, sir.
I
Yes.
suggest
Let
Thiago,
us
if
do
you
it
can
in
do
the
it, you
following
do it.
way. I have an email exchange with Panchanan Huntia.
yes.
Let
he's
us discuss it through email
there. Okay.
via Mr. Huntia.
Yes,
Okay,
yes.
okay.
Yeah.
Yes, yeah.
He's here, right here.
Is here.
I think we should do
Yeah.
Good. Yeah, I see.
Yeah. We are all sitting in the same room and talking.
Uh-huh.
Yeah.
Yeah, in fact, I am interested to do that. Quite interested. Suri, it is very right question,
Yeah, thank you.
which moves us in proper direction.
Yeah. One more small request. I may be, if I'm lucky, visiting IIT in January, but what date are you coming? Any idea?
Well, the conference will start on January 8th, and it will finish by January 13th. Before that, I will be in Goa. But in
okay.
Goa, I will be only a few days and will be busy because Tanusri will make us
okay.
very active.
Okay, thank you. I am not sure of my dates. Let me think. Yeah. Thanks a lot.
Yeah.
Okay.
Okay.
Yes. Any other question from the audience? Okay.
I have a question to organizers.
Yeah.
what can be weather in Chennai in January?
Oh,
Is it
Jan-
will be as cold as in Russia?
No, beautiful.
Oh,
That's where we go.
not-
Beautiful weather.
good
It
weather.
will be minus 35 in Moscow.
Here it is.
If you, Professor Vasiliev,
Yeah.
if you can bring that weather to Chennai once, we'll be happy. Minus 35 is not required. At least bring -5.
No.
Yeah, but what
won't
will
come
be what will be temperature in Chennai in January?
25, 28.
No, it'll
Yes,
be
that's
it'll be very pleasant. Night temperatures 21, 22. Day temperature
Excellent.
26.
Very
That-
good.
Yeah, that is the right time for you to visit. I think we should come. Last time you came in December, I suppose. November or December it was in 2015.
I see. Okay.
I think that.
Okay. So probably that's all of my presentation.
Okay, thank you very much. No other
Let me
questions?
thank you once again. It was just a pleasure to see many people whom I know personally and other people. So
Yeah.
thank you.
Thank you
Thank
very
you,
much.
thank you
Thank you
very
very much.
Thank you very
Thank
much.
you. Hope we'll meet you in January. We'll meet.
Dr. Suri,
Okay. Bye-bye.
Contact. Suri,
Bye-bye,
Professor
take care.
Suri.
Dr.
Yes,
Suri,
please.
if you are planning to come in January, you have to tell us the dates.
I
There's a
know
guest
that.
application.
I didn't want to butt in like this. Today I'm going to write an email to you. I hope you'll read it.
Yeah,
Because
I'll
this
read it.
Professor Rao is extremely busy guy.
Okay. So I have to switch off. Bye-bye.
Okay, thank you very much. Thank you. Thank you.
Thank you.
Thank you.
Bye-bye.
Thanks a
See
lot.
you. Bye-bye. Thank you.
I enjoyed the talk. Thank you very much.
Good,
Thank
good.
you.
Thank
Thank you very much. We'll
Okay.
see you in person in January.
Yeah.
Okay.
Bye-bye. Take
Bye-bye.
Bye-bye.
Okay.
Bye-bye.
Hope
Bye-bye.
Tyagu is doing good work. Yeah.
Yes.
Hello, Tyagarajan.
Yes,
Hello.
sir.
எப்படி இருக்கீங்க?
Thanks.
Okay, very good. I'm happy to see you.
Yes, sir. Sir, we will meet you when you are coming here.
Yeah,
in
I
January.
hope,
Yeah.
everything depends not on the plane ticket, depends on my doctor nowadays.
Oh, I see. Yes. Anyway, let's hope. Let's
Okay.
hope he will give permission for you.
Thanks a lot. Yeah, okay.
Okay. Bye-bye, sir.
Bye.
Bye. See you.
Okay, bye. Thanks a lot. Bye.
Okay, thank you.